In this video, we are trying to find out how can we validate our model. So far, we have already coded up an ant model, and we are able to program the individual ants' behaviors, and now we can use model to simulate the ant colony as a whole, how would they behave. But how do we know the model itself is validated? How do we know the model itself can actually simulate the real world, the real ant colony dynamics? The model can validate itself if our model can produce some complex patterns, and those complex patterns are similar to those in real world. If these two criteria satisfies, we say our model validates. Let's look at two examples. First is based on our understanding of complexity. We say something is complex because the system as a whole is greater than the sum of individuals. In the case of food gathering efficiency, ant colony as a whole has greater food gathering capacity than individual ant food gathering capacity multiplied by 100 times. If we can prove that is true, then probably our model is validated. Let's have a look at some real examples. We designed two examples. One is by a single ant by itself for 1,000 iterations and simulate 100 times. And we can calculate the average food gathering for that single ant. That is 3.71. So multiply 100 ants, and the total food gathering capacity would be 371. And another experiment is 100 ants as a whole, as a system together for 1,000 ticks and 100 simulations. The average food gathering ability would be 393, which is more than the first experiment. But the difference is only 6%. So it may not be that huge. But if we can modify our model a little bit, making this model slightly better to simulate the real world by changing the evaporation rates from 6 to 3, then the figure will change. The first experiment will be 333, and the second experiment will become 390, and the difference becomes 17%, which is a lot bigger than 6%. And if we change the diffusion rate from 88 to 60, the difference is still very high, which is 14.6%. If this kind of difference is real, now we can say the ants colony as a whole can produce bigger impact, has a bigger capacity than any individuals, and sum it up. And if this proved to be statistically significant, then we say, yes, our model is producing some real complex pattern. And for the second example about how ant colony as a whole reacts to food piles of the same distant amounts, we already did experiments in previous video demonstrating that if we set the parameters correctly in the correct range, then our model is able to reproduce the phenomenon that the ant colony as a whole will choose one pile of food over another, or they will finish one pile of food and then the other, instead of doing two piles of food together. But still, we need to experiment it many more times in order to find out whether it is statistically significant that our model is able to behave in a real complex way. And as the research into the ant behavior further, biologists may observe even new phenomena, new complex patterns. And if that happens, our model's parameters need to update itself in order to produce not only the old complex patterns, but also the new complex patterns. So in the process, we may need to experiment on the effects of different parameters of our model to get a feel what exactly does different parameters do. And also we need to do a lot of search for the appropriate parameter values in order for our model to produce all sorts of complex patterns in the real world, as observed by the biologist.